Section 2.3 is on page 48, talks about linear equations. Recall linears is when you have y and its derivatives not raised to a power or multiplied or divided by each other. So this is a linear equation. There's a derivative, a y, no y, a derivative y, no y. Those are two examples. So consider those two. Those are non-separable equations. So section 2.2, the traditional calculus cannot solve this problem. If you glance at this for a minute, can you guess what the left side looked like? Look at that. This says 3 plus t cubed this says 3t squared. It seems this is the derivative of this, and this is the derivative of this. Wouldn't you say that this is the product rule of the quantity 3 plus t cubed and y? If I was to take a derivative of this, wouldn't that be derivative of the first, which is 3t squared times y, plus 3 plus t cubed, and derivative of y is dy dt? And what do we know? If I integrate, wouldn't an integral with respect to time undo that derivative? Wouldn't that simply be y times 3 plus t cubed? And the right side will be 2 add 1 to the power t squared plus c. And wouldn't you be able to get y to be t squared over 3 plus t cubed plus c over 3 plus t cubed? So I'm able to solve the equation. Initially I couldn't, but by recognizing this is the product rule, I could. And look at this second example. Do you see that it's the same idea? If I take a derivative of this, it's right there. And if I take a derivative of this, it's right there. So this is again the product rule. Somebody must have taken the product rule of the quantity y times 2t plus 5t to the fourth. If you take a derivative of the first times the second is right there, plus the first times derivative of the second right there. And if we could figure that out, then if you could integrate with respect to t, the integral will cancel the derivative and you're left with y times 2t plus 5t to the fourth equaling, and this is 7e to the t plus c. And again, initially I couldn't separate this and solve it using calculus, but if I recognize that this is the product rule, then I could. Well, guess what? It turns out if you are looking at a first order differential equation, oh, where did that come from? First order linear differential equation. The key to make sure that's a 1, if you have a derivative plus y and the constant on the other side, if you let u equal e to the integral of this p of t and multiply both sides by u, this would become the product rule guaranteed. And therefore you could solve a problem that you couldn't solve before. So if I look at, okay, that's part of the deal, that's okay. If I look at some problems in the book, on page 54, we're looking at the first set of problems. It says, determine whether the given equation is separable, neither, linear, neither, or both. Well, let's see. Is this separable? This is a function in terms of t. So if I look at that, I would say this is separable. I can't separate this. So this is not separable. Is it linear? With respect to t, I have dx dt. I have x. That's the dependent. X. the derivative of x, x, and e to the x, so that's going to be neither. It's not separable and it's not linear, so I can't use this trick on it. I have to use something else. Problem number 4, if I glance at this, is this separable? Well, no, I can't separate those and those. There's no way of separating those. Is it linear? Y, there's a y that's a t, y prime, a y, yeah, this is linear, which means I could solve. And if I look at number 6, this is not separable, I can't separate it. But if I look at r, there's the r prime and r and no r, this is linear. Now, I want to solve 3 of these problems. It says, obtain the solution. You could use whatever you want. So on number 8, I'm going to start with, let's see how this works. Remember how that setup worked up there? I want that to be a 1. I'm going to do that all throughout the course. Minus y over x equal 2x plus 1. And notice, this is linear in y, and it is a first order. That's why you really need to get those on one side. We call it the u factor. That's what I call it. The u factor is going to be, let me use green, e to the integral of negative 1 over x dx. So u is going to equal e to the negative natural log of x, make that a power. U is going to equal e to the natural log of x to the negative 1. So u is simply 1 over x. If you multiply both sides of the equation by 1 over x, guess what happens? This becomes 1 over x dy dx minus 1 over x squared y equaling 2 plus 1 over x. And this is really, if you think about it, 1 over x times y prime. If you take a derivative of y, it's right there. If you take a derivative of 1 over x, it's right there. So if you integrate with respect to x, that is 1 over xy, that's a nice y, equals 2x plus natural log of absolute value of x plus c, and y equals 2x squared plus x natural log of absolute value of x plus cx, and there it is. And if I look at the next problem, problem number 12, I'm thinking, well, let's see. If I get dy dx plus 4y equaling x squared e to the negative 4x, again, that's not separable. I can't separate those. But what I could do, I could say that's a first order linear differential equation. So u is going to equal e to the integral of simply 4 dx, u equal e to the 4x. And now if I multiply this by u, this will be e to the 4x dy dx plus 4e to the 4xy equal x squared. And I know that somebody must have applied the product rule on e to the 4x times y. And if I integrate to undo that product rule with respect to x, this will be y e to the 4x equaling x cubed over 3 plus c, and y would be 1/3 x cubed e to the negative 4x plus c e to the negative 4x. And if I tackle number 14, this is already set up, except there's a catch. I need this to be a positive 1. This is not a positive 1, so make sure it is. Divide both sides by x, and this is really 3y plus 3x squared. So when I divide, that's 3 over xy, and if I move this to the other side, equals negative 3x plus sine of x over x squared. So there's my p positive. U is going to equal e to the integral of 3 over x dx. U is going to equal e to the 3 natural log of x. U is going to equal x cubed. So if you multiply this and this by u, which is x cubed, that's going to be x cubed dy dx plus 3x squared times y equaling negative 3x to the 4th plus x sine of x. And this is nothing more than x cubed times y, a derivative. And to undo that, I integrate with respect to x. I'll get yx cubed equaling negative, add 1 to the power, 3x to the 5th over 5 plus, and here if I let u equal x, du is dx, dv is sine of x. If I let u equal x, du is dx. If I let dv equal the sine of x, dx. If I integrate, v is negative cosine of x. So this is u times v negative x cosine of x minus the integral of negative du. I'm getting yx cubed to equal negative 3x to the 5th over 5 minus x cosine of x plus sine of x plus c, and y would equal negative 3/5 x squared minus cosine of x over x squared plus sine of x over x cubed plus c over x cubed, or cx to the negative 3. And the last couple of problems are the same idea, except they have initial conditions. So number 18, if I glance at that, it says solve the following problem. Well, you say, okay, no problem, this is not separable. If I let u equal e to the integral, and there it is, 4 dx, u would be e to the 4x. This is dy dx plus 4y equals e to the negative x multiplied by u. That would be e to the 4x dy dx plus 4e to the 4x times y equaling e to the 3x. This is e to the 4x times y prime equal e to the 3x. Integrate, that would mean e to the 4x with respect to x times y equal e to the 3x over 3 plus c, or y equals e to the negative x over 3 plus c e to the negative 4x. Okay, we can do that again. We can do it again. And if I take the initial conditions, if I say, well, let's look at that. Y of 0, if I put a 0, that is 1/3 plus c, that equals 4/3. So c equals 4/3 minus 1/3, 3/3, which is 1. So y equal e to the negative x over 3 plus e to the negative 4x. And that's pretty much it with initial conditions. Nothing different than what we did, and I want to tackle one more. And the same deal, I look at this, again, make sure that that is a 1. That is a 1. So I'll move the 2 over, and I notice it's 3 over x. If I let u equal e to the 3 over x integral dx, u is going to equal e to the 3 natural log of x. U is going to equal e to the natural log of x cubed, which is x cubed. So I have dy dx plus 3 over xy equaling 3x minus 2. If I multiply by u both sides of the equation, I'm looking at x cubed dy dx plus this is going to be 3x squared y equaling 3x to the fourth minus 2x cubed, and this is the derivative of x cubed times y, and if you integrate with respect to x, this will be x cubed y equaling, that is 3x to the fifth over 5 minus 2x to the fourth over 4 reduced plus c, and y would equal 3/5 x squared minus x over 2 plus c over x cubed. I just need to find what c is, and y of 1 equal 3/5 minus 1/2 plus c, and that equals a 1. So clear the fractions. 6 minus 5 plus 10c equal a 10. So that is a 1. 10c equal a 9. c equal 9 over 10. So y would equal 3/5 x squared minus x over 2 plus 10 over x cubed would be the solution to this